So the lecture today is about alignment and translation. The objective, the learning objective today are primarily one about multimodal alignment. I want to expand. We talked about the dynamic time warping. We also studied the attention-based mechanism, but I also want to give you a few more, also specifically for speech and speech recognition. There are a few approaches. There's one specific one on CTC that I want to discuss. And then I also, from alignment, look at one more specific for video, although I think it can be generalized eventually to multimodal, is on temporal cycle consistency. So these are somewhat a little bit more unimodal, but again, with the idea to expand to alignment to multimodal. And then I want to look at the translation, and specifically I would like to study visual question answering. I'm picking it specifically because image captioning is great, and I think has brought a multimodal together in a very nice way. But visual question answering address one of the key challenges on the evaluation side. And so a lot of interesting work came following that. So I'm going to use visual question answering to introduce a lot of the other work that I want to talk about, like co-attention, stack attention, and also neural module networks are a very interesting way to bring domain knowledge and expertise in those neural architectures. And some people went a step further and took neural module network and extended it to make it even more interpretable, and what the neural symbolic learning is doing. And finally, I wanted to show some applications. I think sometimes it's interesting to see that, specifically because speech and video translation is quite an interesting topic. So that's the lecture today, a little bit more about speech and vision, because we studied language quite a bit, but also studying the translation. So alignment, I would like to talk about alignment specifically for a second for speech recognition. I know we studied, as I just mentioned, language and vision quite a bit. When we look at speech recognition is a multimodal task, at least in the way we approach it in this lecture, in this class, in this course. And it goes from an acoustic signal, a speech signal, all the way to language. And it's really interesting because we go from it's a translation, and we're translating from acoustic all the way to language. But the issue here is that we are going something that's very high granularity, like very fine grain, like the audio signal, to something that is, you could almost call discrete, like the language. And so it's a very interesting translation process because of its importance also for many applications and how humans are communicating through speech. It has been an interest for a very long time in AI. And so there has been very well established pipelines. I'm going to just give one of these inspired with some earlier tutorial, is like, how do you go from something that's very raw audio, if you remember, is just a 1D vector, and you go all the way to words. And to go there as a first step is the challenge of how do you represent the audio, how do you represent that? And if you think and remember one of the earlier lecture, how do you represent audio as the first stage, like going beyond just a vector, raw vector? Spectrogram was one of these approaches where you look at the frequency. So taking a sliding window of audio, like let's say maybe 10 milliseconds of audio, and looking at the frequency during that 10 millisecond, how much, 20,000 hertz, how much, and that's what you would do, like with something like a fast Fourier transform, for example. And then a spectrogram does it over time. So you have both time and a frequency there. So this has been studied a lot. And as I mentioned, there's been extension to that also started to look at how the ear is doing this and start looking at it not just as every frequency exactly the same, but you look at some bank of frequencies, like filter bank, and the mel frequency, the MFCC features are one example to that. When it gets closer to, at that point, I think we're still very like speech oriented, where like the magic, in a sense, that goes from speech to language is a lot in those next two steps. The first one is to start classifying the frames. And so it use often the word frames because it's a local acoustic observation. We'll call it a frame. And so we want to classify them. And classifying, you could classify, is it a word? Which word is it? But they, a lot of the work in both speech and linguistic have studied like the phonology. And so we start looking at that point, looking at phonemes and detecting what each of these local in time, how each of them sound, and each sound is a phoneme. And so you get finally an output, and the different colors here are the different colors, the different phonemes, and each language, spoken language, will often have a very concrete set of phonemes. And then from these phonemes, which will be, let's say for this, we'll call them Q, we'll want to get from the set of phoneme, we want, from these initial set of H frame connected, you want to get to the, what are the contiguous phonemes. So one here is a prediction at every frame, but eventually you want to make a final decision that this is the same phoneme. And eventually you will want to go from all of those phonemes to words. And that's usually through a lexicon model. And I'm not going to discuss it as much today, but this is, and that the language model we discussed quite a bit. But this is a like a specify, like what are words made, what are the phonemes that made of word. And here you're like, what are the words that are close to each other? What are the, because W is a vector. So what are the words that are likely to be next to each other? And if you remember, when we look at word2vec, we looked at these, we look at like either predicting the next word, or we'll like fill the blank kind of scenarios like in BERT. So all of these comes in together. And so when we discuss and we want to predict the most the most likely words, this could be a very interesting but very complex pipeline. And some of them are deterministic, as I mentioned. So there's been a lot of work on feature extraction and lexicon. But the middle part is where there's a lot of interesting work on alignment, on sequence labeling, which is the first step, but also aligning them to the phonemes. That's a problem. And so if I talk to you about sequence labeling and alignment, how can we solve this task? My input is a spectrogram, my output is a phoneme. I know that many samples will map to the same phoneme, so it's a many to one kind of mapping. So how can I solve, how can I predict this set of phoneme? And I just want the phoneme is possible. Like I would like to know that all of these together are the same T, and all of these together, although this exact for the spectrogram may not be the match with this, but like tomato, pronounced maybe a little bit of a French way. But yeah, so a first way to do it will be a sequence to sequence model. It's like a very like 101 machine translation, going from one language to another language. I embed my first modality, in this case, speech. I get my intermediate representation, and then I have a generative model that will simply go ahead and generate these different phonemes one after another, all conditioned on that initial seed that came from the embedding on that. And this will be done, as I showed here, as a recurrent neural network, or as we know, also these could be maybe a self-attention models like a transformer, as we discussed. Talking of transformer, we could also make it as an attention base. So in the case of an RNN, we can bring the attention. And so instead of embedding my spectrogram only once and making it such that there's only one time that I encode the spectrogram and then use that to create the series of phonemes, I could go at every new time I want to get a new phoneme and decide where to focus on. And these are one way, but what if I wanted to just do sequence labeling with an RNN right away? One way will be to get the label at each audio, but then I will miss that extra step, which is this like many-to-one alignment. And so I wanted to share an approach and a loss function, and specifically an approach to how do you handle that many-to-one alignment. And this was, that got very popular in speech recognition. It gave a really strong performance, and that's a little bit why I want to bring this. Also, because it may give you some intuitions on how to extend that kind of work. But CTC, which is it's a term that was brought by the authors of this paper of connectionist temporal classification. It's kind of quite a long name, but let's just call it CTC for now. And this has been up to now. Now I will say now we see approaches that don't use it, but up to now it was used with a lot of these deep neural network architecture for automatic speech recognition. And these, a lot of them were either simple convolution, a few layer like deep speech, which is still state of the art up to maybe a few years ago, but yeah, but it was quite strong. And so it was convolution, it was a bidirectional and then fully connected. But the key aspect was how do you do that many-to-one mapping, that alignment? Because I have on one sense, very high frame rate, very different granularity between my modalities, very different granularity, and how do I handle that? And so to formalize this mathematically, the X will be at a frame rate, maybe at, let's say 20 Hertz, I compute my spectrogram. But the phonemes, like if you say that maybe you speak 3 or 4 words per second, each phonemes, maybe like more about 10 to 12 phonemes per second. And the goal is to take, and you may even have higher for the number of frames for this. And so you want to do that many-to-one mapping that I just discussed. And so you don't have the same length, and you want to define over the space of label. The space of label here will be the phonemes. And so we want to do 2 things at the same time, both doing the many-to-one mapping and at the same time train a whole model or classifier, as they call it in the CTC. So the loss will be more of a typical loss, the negative log likelihood, and that's defined over the probability or the score over the phoneme. But the question is how the rest of the model works and how can we do that many-to-one mapping. And so to explain this, I'm going to go through all the steps that a CTC implements. But before CTC, I had already done some scoring. And so it will maybe with an RNN, or in the case of deep speech, we saw all of the layers. And so, but let's suppose I have them, and then I will just do the typical normalization. And so from those normalized output, I get this nice distribution. And this distribution is over all possible phoneme. So here I draw them as if there were only 5 of them, but if you remember, there may be 50 or 20 of them. I'm just showing 5 of them. And so for each of those 50 or 100 of these, I will want to predict which phoneme can I currently hear. And so I can just plot all of these different phonemes. So if my language, like English, has a certain number of phoneme, that would be the number L, the number of phoneme. and T is over time. And then I will do this extra one, which is for blank or no label, maybe a silence or just something else that I don't have a label for it. And so the idea here, which has a flavor, we'll discuss a little bit more when we talk about graphical models, but the idea of looking at the path over this activation, because what this is I have almost a probability because it has been normalized, and so I have a probability over all of these labels. And now I want to know what has been spoken. What did the person really speak? And it's possible that I'm more than once on the same phoneme, and maybe there's a pause and then there's another phoneme. And so I want to be able to like T, and there's a pause, and then ah. And so I want to know what is this optimal set of phoneme. And so I can have a very large set of paths. In fact, there's, if you look at it, there's every possible path that I could imagine. It's not infinite, but there's a large number. Luckily, it looks a lot like things like optimizing an HMM, which hidden Markov model, which we'll discuss more in details next lecture. But this, you can compute relatively easily probability of a specific path. I have one path in this. What is the probability of that path to be? And so this is the probability over the path that you can given the input X. And now I'm still not yet decided completely because I have a probability of one path. And then I want to predict the labels. The labels will then be a chain rule of then the probability, the temporal alignment, I'm going to talk about it in a second, time each of the probabilities. So I have the probability of a path, and then that path, I need to go from a path to very, very specific set of phoneme. And that's really interesting because in this case, you could have maybe tried to learn it. And I want to say that's probably the approach that in the neural network world, we always think, hey, I need to learn everything. Everything has to be learned from scratch. But there may be knowledge we already have that we can add to the model. And so some components of the model may not need to be learned or relearned again. And that's a little bit the approach they use here. They said, let's remove all the blanks. Let's repeat all the labels. And that's a very simple set of rules. And then once you have this, and then you can do an optimization to try the most probable sequence labels. And then, so how do you optimize this? Because you have all possible sets of paths. There's two ways to optimize, or at least there's more than two, but there's two ways originally proposed. And then one is just to take whichever is the most optimal path here, and then from that most optimal path, just use my rules, my handwritten rules, and then get whichever the optimal phonemes are. The more classic way, if anybody who's done HMM, will be to use dynamic programming and then do a forward-backward algorithm. It's a really well-established algorithm if you have in an HMM hidden Markov model and you have all of these states and you have also probabilities over those states and you want to know what is the most likely sequence of states, that will be a forward-backward algorithm for that. The extension to that will be belief propagation, which is a generalization of the forward-backward algorithm. And it works with a forward set. You kind of pass the messages, and that's what you accumulate through those alpha. And then you pass them again, you accumulate to the beta, and then you multiply, you integrate them together. I want to show one thing interesting with CTC. I know this graph is a lot of information. So you have the raw waveform. And what I show here is a typical output of before CTC. Like what will be the typical output, which is also what kind of is the input to CTC in a sense, is like predicting at every point in time, trying to predict the phoneme and simply like working from it and getting to, for every speech frame, predicting the phoneme with maybe some smoothness to be sure that things are close to each other, are similar labels. One of the challenges when you predict that at the frame rate is that even though you maybe have predicted correctly the phoneme, if you make any error a little bit, let's say before, and you got it a little bit wrong before or after, that will get penalized. The model will get penalized for those misalignment in the boundary. Yes. So the idea here is that you don't want the CTC. If you see the big difference in the predictions, is a lot more peaky, and you have to ask yourself, why is it so peaky? Because CTC focuses on the phoneme transitions, and so it's looking at the transition. And if you're looking at the pipeline for speech recognition, in that case, I don't really care that the phoneme was spoken for a very long time, like hello or hello. I mean, they're both the same word, hello. And so as long as I know which phonemes happened, then I can use that information. And I think this is the key, and the part I like the most about CTC is that it focuses on transitions, and looking at, and for the task of speech recognition, this was sufficient. And so when you look at alignment and you look at these temporal tasks, you have to ask yourself, do I really need to know exactly the boundary of everything, or will it be sufficient to only focus on the transitions? And CTC is one of these approaches, and there's been a lot of extension to that since then, and there's been a little bit of work also before on transition, but I wanted to make you aware of these other approaches. I want to also I would like to talk now, not in French maintenant. I'd like to talk about not just speech, but also video alignment. And we discuss it with dynamic time warping as an example for that, where you're trying to align two videos. It could be from different modalities, or it could be just two videos that, you know, like two people doing the same action. You don't know exactly when, they maybe not aligned perfectly, and the action may be done differently, like maybe a different version of this, but you want to align it. And so we talk about dynamic time warping that solved this through dynamic programming, and that was one approach. This is great, and I know that some students had asked, like, is there a differentiable version of it? And we added it as a reading assignment. It's an interesting extension of the dynamic time warping. But I also wanted to go a step further and look at, like, what are the how to take advantage of neural representation. Like we discussed in the first like 3 weeks ago about how you can learn neural representation. What I mean by learning neural representation is we have a frame and we can encode a frame in such a way, and this is the value of the encoding, and in this case the encoding is only one dimensional. In a normal encoding, the dimension will be multidimensional, like a CNN, maybe 700 or more, or 3000 of these dimensions. And so I want a way to embed, I want to take advantage of these neural representation, and I want to take advantage of it in such a way that when I learn this, I will also be able to emphasize and also solve for the alignment problem. So I would like, at the same time that I'm learning the way to encode images, I would like to also at the same time learn to align between images and between videos. It could be a set, and in this case, we'll talk about videos, like 2 videos. And there's a big premise, because a lot of people would call it self-supervised learning, and that's how the authors also call it. But you have a big premise that you have paired data and video sequences where there's paired data. Pair in the sense that you know that there's some of the same actions that are happening in that, and that alignment will be possible at some level. Although there's extension, you could imagine, where you look at outlier rejection, where there is, in fact, where you could make that premise loosen up a little bit. But for now, we'll say we know that these videos are possible to align, but we don't know how to align. And through that process, we want to learn to embed the videos in such a way that we get the embedding that is telling us about better what the actions are, and like a better embedding. So we both at the same time want to get better embedding and better alignment at the same time. And so how can we do, and what would be a loss function? What should be an interesting loss function to encode this? And the loss function for that is one that I thought was really intuitive and really interesting. Intuitive once you get it, but it's one of these things. I mean, ideas sound so simple once you've heard about it, but it's really great. And I like the intuition behind this idea. It's like temporal cycle consistency. That's the name the authors gave to this approach. And the basic idea is my closest neighbor should also have me as their closest neighbor. You want them to be as this. So a cycle consistency will be if I myself, if I believe and I look which I'm one frame of sequence B, let's say, and so I look at all of the frames in sequence A, or let's say video 2, and then I look at one frame, all the frame for video 1, and I look which one looks the most like me. Which one looks the most like me? And I will suppose for now, let's say that it's not optimized that way, but let's say it was optimized iteratively. Let's say I have already an embedding for both of them, and so I could imagine look like, hey, my embedding, and look at those, and you could do something as simple as a cosine similarity. And so you look at, hey, which of these are the closest to me? And so here will be a 1DTSNE that will be shown here maybe. And so and then I go and look at all of the, for that closest one to me, I look at, hey, what frame is the closest to you? Like from your perspective, look at all of the other frame and look at which one is the closest to you. And if it's not a match, I'm going to penalize it. And so I want as much as possible for all of us to be as consistent in this, and as often as possible, whenever possible, we want it to be as consistent as possible. And so this is the idea of the cycle consistency, and I'm going to explain it mathematically in a second, but I wanted to give you the high level. And so if you have 2 videos, for every frame, I'm looking at in the other one which frames is the closest to me. And then I can look for that frame that's closest to me, which other frame from my neighbors did they prefer me or not? And that's kind of the idea. So mathematically, what it looks like is, for now, maybe they share an encoder. I talk about it as 2 different encoder, but let's, for now, in a multimodal case, which I don't think I've seen yet, but you could imagine an extension of this work to have a multimodal case. But for now, the unimodal case, you could imagine is the same modality, so encoders are going to be the same. And so each frame will have a representation like 3,000 dimension vectors. And then I will start a multiple step process. The first one is for a specific frame. In this image, I do it the other way. For a specific frame, I will look at all of the frame in the other sequence, or maybe within a window. And then I will see which one is the closest to me, like some kind of similarity between the two. And then that will give me my soft nearest neighbor. And the soft nearest neighbor, what I will do for that soft nearest, and it could be a hard nearest neighbor. It just empirically works. The hard nearest neighbor will say, hey, this person is my nearest neighbor. The soft one is a typical like kind of attention based. It's just like saying from all of them, what is it that looks like me? And so there may be many frames that looks like me here. And so if there are many frames that looks like me, I'm just going to take an average of all these frames that looks like me. And then what you take is that average frame that looks like me. If it's a soft, if it was a hard, it would be just that frame that looks the closest to me. I take that frame, and then I will look all my neighbors. What is how similar they are to that soft neighbor, like how closer are now. And as you can imagine, what you will hope is that it is as close as possible to me, but in reality, it may look slightly closer to other frame. And if it is, I'm going to penalize it. And so now this is going to be part of my loss, is because I will penalize that distance I. Sorry, it's really hard to see probably on the Zoom, but this is I. So I will penalize the distance between the two, normalized by some kind of depending on how well, like if it's a very peaky thing, like if it's a peaky distribution, that's very different from if it's a flat distribution. And so that's what this is going to add to it. So the mean of that Gaussian and this is just for normalization. And I may have just because I want to have maybe more peaky or like I want to put some regularization on from that. So this is the temporal cycle consistency. It's a really nice, it's a nice and intuitive. What was really nice, and I invite you to read the paper. I don't think we put it as a reading assignment, but it's a nice optional one we could add to put there if it's not. I forgot if we put it already or not in the reading assignment. But yeah, this is nice because not only can you do the alignment, you also learn an embedding, and it turned out that you can later on use this embedding with only one video and may be able to do good also action recognition, for example. But here in our case, the penalty will be done with that term. So they can do that also and see which frame looked the most like me. And so take a video and run it with the temporal cycle consistency and then see which frame is the nearest neighbor. And then what's really nice is that they should semantically be similar. And so that's the hope, is that my embedding that I learned is even more. Previous embeddings, if you remember, most of the embeddings before were for object detection. Like, is it a glass or not? Here, it's not just a glass, but it's about the appearance of the glass, of and that's the interesting aspect here, is that it gives more guidance in the visual embedding, so that this extra guidance hopefully will make an encoder that's a little bit closer to a more meaningful or semantically meaningful embedding. And then the interesting part was, like, if you have something you expect, like a video of the way you should be doing something, if there are frames that are just not similar to any of the other frames, you could call it an anomaly. And I would like to call more as a research question for you. How could you extend this idea to multimodal? And what will be the challenge here? And so I want to keep it open-ended, that question. I give you some hints of the answer. Definitely the encoders will be different. Like if you have, you'll have a different, like let's say for images or for language, we'll have different encoders. But the important thing is also the similarity. So how similar my closest neighbor will also be challenging, and that's maybe why you will need to do some of the approaches. Maybe you do a joint embedding where everything is together, or if you decide to have them more as coordinated, then the similarity function would be very important. How do you find that the two are similar? I think that's very interesting. I want to now switch to the second half of the lecture today and talk about the concept of multimodal translation. This is the idea of the typical image, the translation, multimodal translation has been image captioning. As I mentioned in one of the first lecture, one of the challenge with image captioning was that it was very hard to evaluate. You could have many different captions, but then at the same image, maybe people decide to focus, yes, on maybe the most salient object, but you could also suddenly decide to talk about other object, and both are in a sense valid. And so the interesting extension of this, which was proposed, is the visual question answering. The visual question answering goes with the idea that you have a question, is the skateboard airborne? You have an image, and then you have an answer, and different version of VQAs, and then you have, for example, now extensions like text VQA. I think some of the teams are working on this. Like there have been a lot of extension of VQA to make these either longer or a different flavor. But in the original one, the answers were relatively short, so short that in fact, and some of them were repetitive, so that they were able to even like get a vector of the 1,000 most occurring answers. And so they were even able to bring it as not even just a text generation, but as a classification problem. And so from an evaluation perspective, if it is 1,000 labels and we're having some prediction over those, we know how to evaluate that part. And so that brought interesting, at least it improved on the evaluation part. Now it's a translation, but it's interesting because it's almost a two-way translation, and or three ways if you say. One is you could say I'm translating from language and then to image to eventually to an answer. I'm looking at the image first, I'm looking at the question, and then at the answer. So what is the flow a human will do, and what is the flow a computer should do, I think is quite interesting. So if you had to put attention in this case, like use some of the concept, because we probably want, it's a translation, but it's also an alignment problem, because I want to align some elements of the image with some of the element of the question. And so how to do this, and how can we use maybe attention? The typical way you probably, and that's the way I introduce attention in the earlier lecture, is to go from question to image. Like you are, you have different words, and you will try to ground or connect these images or objects. Let's say we have an RCNN that ran over the image. So you have a bunch of instances of objects, and then you have instances of words, and then you want to match the two together. So we could you could have, based on the language, you could maybe embed the language and try to see which object to focus on. Or you could also look the other way around and look at the image, maybe what's center, what's bigger, or a specific type of image. Maybe the people are more likely to talk about a human in the image. And then see what words are important in the question. And so which one to use? As you can imagine, someone nicely decided to do both. And that's called co-attention. And the idea here, and this is just a depiction of it, but the idea here is I can embed my question, but I have many entities in my questions. I can find a way to embed and get a context and then use that to you embed my question, find my attentions, and then find a way to embed it, and vice versa also for this. So you can get the co-attention going back and forth. So the question can be embedded and the image can be embedded at the same time. And then you get the visual embedding that's contextualized. And as you can see, now these days, how would you do that co-attention? It will probably also be with a self-attention, but that's kind of a precursor of this idea of self-attention. The co-attention paper had come also with the idea of looking at it at different level. Like one is a unigram, which is one aspect. One is about the bigram, and one is about the whole sentence. So the question is like, maybe you want to attend specific part of the image based on the whole sentence, or you would like to do the more classic attention based on each word where in the image. And at the end of the day, maybe you want to do all of them. So this paper did both like hierarchically and co-attention as well. I just want to share another extension that had been done and produced, which was the stack attention. So the idea is that, and as we've seen this also in the multi-headed attention, we can stack these different attention. And so the attention of one can be used to the next one, to the next level. And there's a lot of things, and I want to present that, and that's not the main focus of this lecture. I just wanted to give a few more, just because these days we always often go to self-attention model and transformers, but I would like people to be aware of other work before that, both as a precursor of where we come from when we talk about self-attention, but also to think about other ideas you could extend beyond just, and sometimes also your model, maybe just if you go with the self-attention, so many parameters, and maybe for that kind of data, there's no easy way to pre-train, and so there's another reason you should look at those simpler attention models. I often start with simple models, more interpretive, it's easier to interpret. I think there's a lot of value there. But the main thing I wanted to talk about, and why I introduced the VQA, was to talk about another aspect, which is an extension of the attention models. Also, what I like the most about the next part is the idea of bringing domain knowledge. I know something about this domain, and instead of training everything from scratch, very from bottom up and like very data driven, let me use some knowledge I have about the problem and add this. And maybe one of this knowledge is about the syntax of the language, or it could be others, and I'm going to show other ways you can do that. So the approach, and which there's been quite a bit of extension about, is neural module network. And neural module network allows to bring knowledge, two types of knowledge. One is about sentences, like sentence or linguistic knowledge is the question or the caption, or but let's say for now the question can be splitted And instead of using a simple RNN to answer this question or embed this question, there may be some knowledge I can get from how this sentence, this question is syntax, its syntax and its structure.